As promised, we'll now look at Albert Einstein and 1879 to 1955. And these are still lectures from the notes of Father George the Schriver. So who is Albert Einstein? Before we start looking at Albert Einstein, it's important to be reminded of Isaac Newton's mechanistic and static universe. Isaac Newton said in this quote, "Hitherto I have not been able to discover the cause of those properties of gravity from phenomena, and I frame no hypotheses, for whatever is not deduced from the phenomena is to be called an hypothesis. And hypotheses, whether metaphysical or physical, whether of occult qualities or mechanical, have no place in experimental philosophy. In this philosophy, particular propositions are inferred from the phenomena and afterwards rendered general by induction. Thus, it was that the impenetrability, the mobility, and the impulsive force of the bodies and the laws of motion and of gravitation were discovered. And to us, it is enough that gravity does really exist and act according to the laws which we have explained, and abundantly serves to account for all the motions of the celestial bodies and of our sea. It's worth remembering that it is in this context of Isaac Newton that we actually see Albert Einstein. Albert Einstein, 1879 to 1955, revolutionized the human understanding of the universe and of our place in it. He has two very important theories, the special or restricted theory of relativity and the general theory of relativity, which we shall now immediately dive into with the special theory of relativity. In order to grasp the approach and the revolutionary mind of Einstein, it's important to see what actually has been confronting the scientific community at the end of the 19th century. These are the mere incompatibility or the incompatibility between the newly discovered laws of the electromagnetic field and with the classical Newtonian mechanics. The persons that you have here in front of you are actually Michael Faraday, 1791 to 1867, and James Maxwell, 1831 to 1879. Their research actually puts into question the general framework of Newtonian physics. It's worth taking note that Newton emphasized that the motions of mass particles are unchangeable, operates within the unchangeable coordinates of space and time. Electromagnetic field, and it's worth remembering how the tension, for example, the pull of gravity that changes the path of the moon, the pull of the moon of the earth, and things like that, were things that we've already discussed in the discussion on Newton. But it is in relation to this that the electromagnetic fields didn't seem to behave the way Newton envisioned. They behave quite differently from mass particles in that they propagate themselves through undulations with a speed that equals the speed of light, 300,000 kilometers a second. Moreover, they carry a determinate amount of energy with them. The connection Maxwell established in 1864 between electromagnetic fields and light waves was one of the greatest accomplishments of 19th century mathematical or theoretical physics, although it was already discovered earlier that light traveled at the constant speed of 300,000 kilometers per second, no matter the speed of its source. So this phenomena of the electricity not only left its imprint on the scientific community, it also stimulated business activities. Electricity changed the way people lived. Generators were invented, dynamos suddenly became available in the market, and incandescent bulbs lighted the houses, streets, docks, and railways of the cities, and telegraph connected London and Berlin. It is therefore not extraordinary that Einstein, whose father was a businessman during that time, especially one that is engaged in the manufacture of electronic equipment, was fascinated by the very properties of light waves. At a very young age, he asked himself what would be the consequences of being able to move with the speed of light. This question, innocent as it appears, brought him into conflict and contradictions of the enormous depth within the foundations of physics. As a teenager and already engaged in the private study of the classics of physics, he was dissatisfied with the rote learning, the memory mode of learning at Luitpold High School in Munich. The grades he received in high schools were mediocre. He hated high school that he took an early entrance examination to the Swiss Polytechnic Institute in Zurich and failed. And then, after 1 year of intensive study in Aarau, Switzerland, he was able to successfully complete the same examination. It is then at the Polytechnic Institute that he had the privilege of being taught by Midnovsky. Once he graduated, Einstein took a menial job as a clerk in the Swiss Patent Office in Bern, in Switzerland, and this was enough for him to earn a living so that he could devote his spare time to his thought experiments. The speed of light would constantly be of interest to Einstein. It basically brought him in contact with Newtonian physics. And within the framework of the speed of light, and that it varied depending on whether one measured it from a stationary or moving platform, if assessed from a stationary frame of reference, the speed of light is measured at 300,000 kilometers per second, whereas assessed from a moving frame of reference, it is measured at less than 300,000 kilometers per second. That's why he would say common sense would seem to tell us that if we were to travel very rapidly in some direction, and this is a citation from Roger Penrose's The Emperor's New Mind, and we continue, then the speed of light in that direction ought to appear to us to be reduced to below the beam of light because we are moving towards catching the light up in that direction. The speed, which is now called v, with which we, when sitting in a spacecraft, rush towards the beam of light, ought in this logic to be subtracted from the speed of that beam of light. The resulting velocity, w, should be w is equivalent to c minus v, as we can see in the notes of Father de Schriver. So we have seen already this subtraction and addition at work in Newton's description of the sailor walking on the deck with a mixture of absolute and relative motion. And therefore, we will not expound it any further. But it's also worth saying that it was through worrying about these matters that Einstein was led in 1905 to the special theory of relativity. He was not willing to give up the elegance of what is technically called the equivalence principle, according to which the physical laws remain totally unchanged if we pass from a stationary to a moving frame of reference. And this is something we have learned from Galileo and his experiments. So let's look at the relativity of time and space. So the speed of light remains invariant if one passes from one frame of reference to another frame of reference. Sorry, I forgot not to share the sound. And here, which I will have to pause every so often so that YouTube will not mark it to be a copyright issue. Based on this insight, Einstein will challenge Newton's notion of absolute space and time. And in his popular exposition of the theory of relativity, he gives the following example to illustrate the non-abstract character of time and space. I'm opening my video for purposes of providing a commentary of the said video. Let's watch this video and pause it once in a while. So in the first move, Einstein dismantles the classical notion of simultaneity. He begins with constructing two different frames of reference, a stationary railway embankment and a very long train traveling along the rails with a constant velocity and in the direction indicated in one direction. So he asked the question, if this train would be struck by two lightnings, A and B, that from the point of the observer in the embankment, will it also be appear as that appears as simultaneous for an observer in the train? What is really the what will happen there? No. So the answer to the question is obviously the one in the train and the one outside the train will see it differently. It is obvious that given the speed of the train, the observer sitting in the train will hear a thunderbolt coming from A earlier than coming from B. In contrast to the stationary observer in the embankment who hears them simultaneously. Okay, let's watch this.
Imagine two observers, one seated in the center of a speeding train car, and another standing on the platform as the train races by.
So there are two observers in this example of Einstein, one inside the train, one outside the train, one inside, one outside the train. And the one inside the train is moving towards the direction of the one outside the train.
As the center of the car passes the observer on the platform, he sees two bolts of lightning strike the car, one on the front and one on the rear. The flashes of light from each strike reach him at the same time.
So there you see the distinction. It was passing, and then at the front and at the back, there are two thunderbolts that hit it at the same time. No, and from the observers who take the railway train as the reference, they would say that the lightning A and lightning B occurred at the same time. No?
So he concludes that the bolts were simultaneous, since he knows that the light from both strikes traveled the same distance to his eyes at the same speed.
So there you see also in the presentation, both of the lightning actually approach him at the same speed. And because it approached him at the same speed, you'd see why he'd say they approach him at the same time. No? So events which are here, you would see already why he thinks that it happened at the same time, because he saw it at the same
speed of
time.
light. He also predicts that his friend on the train will notice the front strike before the rear strike, because from his perspective on the platform, the train is moving to meet the flash.
So there you see the flow of the green light, the two light. The one in front actually hit the friend first before the second one did.
At the front and moving away from the flash at the rear. But what does the passenger see? As her friend on the platform predicted, the passenger does notice the flash from the front before the flash from the rear. But her conclusion is very different. As Einstein showed, the speed of the flashes as measured in the reference frame of the train must also be the speed of light. So, because each light pulse travels the same distance from each end of the train to the passenger, she can only conclude one thing. If she sees the front strike first, it actually happened first.
So there. So events which are simultaneous with reference to the embankment are not really simultaneous with respect to that train, and vice versa. This is the
Whose interpretation is correct? The observer on the platform, who claims that the strikes happened simultaneously, or the observer on the train, who claims that the front strike happened before the rear strike? Einstein tells us that both are correct, within their own frame of reference.
So that's the relativity of simultaneity. Every reference body or coordinate system has its own particular time, unless we are told the reference body to which the statement of time refers. So there is no meaning in a statement of the time of an event. This insight actually revolutionizes a lot Einstein's understanding of, our understanding of time. Okay? Before the advent of the theory of relativity, it had always tacitly been assumed that the statement of time had an absolute significance, that it is independent of the state of motion of the body of reference. Yet, as we have seen in the previous example here of the train, the above experiment has shown that time depends on the velocity of the body frame or the body frame of reference. The same is true, therefore, for the measurement of space. Again, if you look at here, if one would measure in the train the distance between the middle of the first and of the 20th carriage, then it would turn out that the measurement of that same distance conducted on the embankment would be slightly different. A priori, it is by no means certain that this last measurement will supply us with the same measurement as the first. Thus, the length of the train, as measured from the embankment, may be different from that obtained by measuring in the train itself. Measured from within the train, the length of the train turns out to be so much shorter. For Einstein, the specific values one gets for the time and distance are clearly dependent on the conditions of motion of the frame of reference. Yet, in spite of that fact, the speed of light is always perceived as traveling at 300,000 kilometers per second. In all frames of reference with their varying speeds, the speed of light is constant and is not in the least affected by either the speed of the object emitting the light or by the speed of the observer perceiving it. Strictly speaking, the embankment on which the measurements are made is also in motion due to the rotation of the Earth. This leads us to the length contraction and time dilation. To corroborate the ideas of Einstein, he recourse to the Lorentz transformations, which describes how measurements of space and time by two observers moving at different velocities are related. Here we can actually see two spaceships. In this example, we can see two spaceships emitting light and throwing that light to each other. Let's watch this.
Two spaceships are traveling together through the galaxy at close to the speed of light. Mounted on one ship is a laser that can fire pulses of light, and on the other, a mirror. The pilot of the first ship fires a pulse at the mirror and watches as it is reflected back. A clock on board measures how long the round trip takes. But now suppose that he does this as the ships are passing an observer on a nearby asteroid. According to relativity theory, this observer sees the pulse moving through space at exactly the same speed that the pilot does.
So there, that's also something we need to pay attention to. So here, no, the motion would change depending on the observer who is looking really at the movement of the light from A to the first to the second spaceship to the second one, no? And here it looks like the speed of light were really preventing measure rods and clocks from coming with results that would actually exceed the speed of light. So if we continue,
Namely the speed of light. But he also sees the pulse traveling a longer distance,
there.
because from his perspective he must add the forward motion of the ships to the motion of the pulse between them. So he measures a longer time interval for this round trip than the pilot does, because
So there, so you see already the motions and why it's very important. So a great many of the effects of relativity are counterintuitive in nature. No wonder that the observers within a particular frame of reference are unaware of the changes in their own measuring instruments. And here, no, in this example of the spacecrafts, each with an observer in them, the spacecrafts fly parallel to each other, each with a relative uniform motion and in the same direction. The point of view of each will be that the other's moving clock is ticking at a slower rate than their local clock, and that the other's measuring rod is shorter than their local measure rod. In other words, when looking at each other's cabin, even the pilots in these spacecrafts will perceive that time is running slower. And what is more remarkable is that their neighbor spacecraft is much shorter than it was on the ground. So, and here you see the twin paradox of relativity. One twin brother remains on the Earth and the other makes a journey to a nearby star. Traveling there and back at a great speed, approaching that of light, upon his return, it is found that the two twins can age differently. The traveler finds himself still youthful, while the stay-at-home brother is an old man. Excuse me. And that's something we have to pay attention to also. So that's the length contraction and time dilation concern. Einstein also regards the equivalence of mass and energy as one of the most important results of his special theory of relativity. Body mass can be converted into energy, and likewise energy can be converted into mass. This convertibility presupposes that mass is not constant. A body's mass depends on the speed of its frame of reference in the same manner as duration and length depend on the speed of their frame of reference. So a moving electron or a massive object becomes more massive when it is in motion with respect to an observer than when it is at rest with respect to the same observer. So in particular, as the speed of the object approaches the speed of light, its mass becomes infinite. Here, the speed of light serves as a limitation concept. It can never be reached by a material object, as an object approaches the speed of light, its mass rises ever more quickly so that it takes more and more energy to speed it up further. So it can, in fact, never reach the speed of light because by then its mass would have become infinite and by the equivalence of mass and energy, it would have taken an infinite amount of energy to go there. To express this interrelation mathematically, Einstein elaborated the simple and now famous equation E is equivalent to mc squared, where E denotes the energy of the object, m the mass, and c the speed of light. Energy equals mass multiplied by the square of the speed of light. Now, this equation also suggests, as the notes would say, the possibility of transforming mass into energy and vice versa. Its most peculiar effect is the transformation of mass into energy, which Einstein brought up in his 1905 paper, Does the Inertia of a Body Depend Upon Its Energy Content? If a body gives off the energy E in the form of radiation, its mass diminishes by E over c squared. So conversely, the radiation that is set free has the power of the diminished mass, a power that, as we now know, may cause a massive nuclear explosion, as this happened with the dropping of the two atomic bombs in Hiroshima and Nagasaki, with an estimated death toll of 300,000 people. The fact that mass is equivalent to energy means that, in a sense, matter is locked up energy. If some way can be found to unlock it, matter will disappear amidst a burst of energy. Conversely, if enough energy is somehow concentrated, matter will also appear.
In mid
The picture of Einstein's space presupposes a special geometry that is very different from the Euclidean geometry. This special geometry was developed by Hermann Minkowski, 3 years after Einstein would set out or release his special theory of relativity. Minkowski is one of Einstein's teachers in Zurich Polytechnic Institute. His fundamental new idea was that space and time had to be considered together with a single entity, a four-dimensional space-time. So, in this lecture at the University of Göttingen, Minkowski says space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. So the best way to understand Minkowski's geometry is to actually explain what he reveals about the light cone, which you can see here in terms of the past light cone and the future light cone in front of you. So that this light cone is in fact a double cone centered at each event in space-time. The upper cone, the future light cone, represents the history of a light flash emitted at that event. The lower cone, the past light cone, represents all directions from which light flashes can be received at that event. Future and past light cones move outward at the speed of light. So, for purposes of this explanation, we can look at the future light cone. This will allow us to grasp what Minkowski has in mind. He'd say it's basically to talk about special relativity, that which was called the event at which the future light cone is centered can also be termed a point of space-time origin. In this scenario, it would look as if a portion of space-time pops up and, as in an explosion, gives rise to particles and to the future light cone that moves outward at the speed of light. The future light cone is the area in which particles enact their history, and since the particles persist in time, they are represented as lines, the world lines. It is these world lines that are going to travel within the light cone. And the world lines of particles that move uniformly are straight, where those accelerating particles are curved. Uh, so a future characteristic of the special relativity is that the more the material particles world lines dash further into the future swelling light cone, which moves outward at the speed of light, the more the clocks attached to them go slower. This again indicates that no material particle can travel faster than light. And that's something we need to pay attention to, especially if we're working on uh, Albert Einstein. Let's read the last paragraph in the notes of Father de Schriver, as they are quite revelatory. He says, ah, never mind. He says, and I'll put it in colored there. The geometry of the light cones with glowing circles make it clear that A, no signal of a cosmic event can reach us that would be traveling faster than light. And B, that only in places that lie within this growing light cone, the emitted signal can be registered. For example, if the sun were to cease to shine at this moment, it would not affect things on Earth at the present time because they would be in the elsewhere of the event when the sun went out. We would know about it only after 8 minutes, the time it takes light to reach us from the sun. So only then would events on Earth lie in the light cone of the event at which the sun went out. Similarly, we do not know what is happening at the moment farther away in the universe. The light that we see from distant galaxies left them millions of years ago. And in the case of the most distant object that we have seen, the light left some 8,000 million years ago. Thus, when we look at the universe, we are seeing it as it was in the past. So we're not actually seeing the present. No? When you look at the stars, we're actually looking at the past. And literally, even when you look at the sun right now, you're actually looking at the sun 8 minutes ago, not as it was now. So for Einstein, the four-dimensional space-time revolutionizes our notion of time. In space-time, there's no longer an independent, absolute notion of time with universal value. The now loses, for the spatially extended world, its subjective meaning. It would be nonsensical to regard our now moment of observation as coinciding with the proper time sequence of faraway events in the universe. So if one looks at light emitted by a star, one can be sure that its very source is no longer at the place where one perceives it to be now. There are perhaps several million light years between the light emissions and our observations of it. And during that interval, the stars certainly changed its position. So when you look at the night star right now, you're not actually looking at the night star as it was now, night skies as it is happening now, but as it happened maybe more or less some 8 million years ago. At least with the sun, it takes 8 minutes for that to happen. But uh, the special theory of relativity is a restricted one. Why? Because it only operates in the condition that that these objects operate in uniform straight lines. General relativity, however, includes the study of non-uniform motions such as acceleration, retardation, and even rotation. Yet, Despite this seemingly simple extension, the truth is it is not. It will necessitate an elaboration of a geometrical theory in which space is curved. And this is an approach that definitely goes beyond Minkowski's geometry of four-dimensional space-time. So, reduced therefore to its essence, the special relativity maintains that the same physical laws hold with reference to a framework when at rest or in uniform motion. Now, one's instinct for generalization would be tempted to extend this equivalence to all sorts of motions. But at first glance, there's little hope of success of this attempt. To give us an idea that the generalization is not immediately plausible, uh, Einstein will actually show to us a case where it is not. Sorry. Let's go to the text of Father de Schriver. Uh, so this is so Einstein construct a scenario in which it becomes evident that a retardation disrupts the equivalence of a state at rest and a state of uniform straight line motion. He would say, and it's worth quoting as it's quoted here by the Schriver, let us imagine ourselves transferred to our old friend, the railway carriage, which is traveling at a uniform rate. As long as it is moving uniformly, the occupant of the carriage is not aware of its motion. And it is for this reason that he can, without reluctance, interpret the facts of the case as indicating that the carriage is at rest, but the embankment in motion. If, however, the constant motion of the carriage is interrupted or changed into a non-uniform motion, as for instance by a powerful application of the brakes, then the occupant of the carriage experiences a correspondingly powerful jerk forwards. The retarded motion is manifested in the mechanical behavior of bodies relative to the person in the railway carriage. The mechanical behavior is different from that of the case previously considered, and for this reason, it would appear to be impossible that the same mechanical laws hold relatively to the non-uniformly moving carriage, as hold with reference to a carriage when at rest or in uniform motion. So indeed, because of the change into a non-uniform motion, the occupant of the carriage no longer feels at rest. The fact that he experiences a powerful jerk forward suddenly interrupts his state of rest, and so the equivalence between a state of rest and a uniform straight line motion no longer holds. As we will see in the following details, the troublemaker is apparently gravity, which was not included in the special theory of relativity. Yet if one takes gravity as a new absolute, then equivalence between a state of rest and a state of non-uniform motion can be established. That's why Einstein undertakes his general theory of relativity. And he begins this one specifically by looking at the equivalence of inertia and gravitational mass. It's very interesting how we should look at this because Newton will tell us these are different. No? Inertial mass is the mass that you'll need in order to move something or to sustain something in motion. And that has been understood as separate and different from the gravitational mass that pulls each other together. However, Einstein would say they're actually equivalent. Let's go to the notes as the notes are more clear along these lines. There. In order to make plausible the new equivalence, Einstein shows in a first move that the gravitational mass is equal to the inertial mass. The two sort of mass already figured in Newton's theory of motion, Inertial mass m measures the body's acceleration as a response to a given force F. No. Einstein, first of all, points to an inconsistency in Newton's theory of gravity. According to this theory, gravity works at a distance through the void, and its effect is instantaneously felt. So for Newton, the gravitational attraction of the sun is immediately felt in the earth. For Einstein, this is improbable for two reasons. One, first of all, he presupposed a communication faster than the speed of light. And second, it ignores the fact that gravity is propagated by gravitational fields, and that creates a distinction. So when reflecting on gravity, Einstein, from the outset, links it to gravitational fields. For him, the answer to the question, if we pick up a stone and then let it go, why does it fall to the ground? For him, the answer to that is simple, because it is attracted by the gravitational field on the Earth. The procedure is similar to a magnetic field that attracts a piece of iron. Yet, in contrast to the electric and magnetic fields, the gravitational field exhibits a most remarkable property, which is of fundamental importance for what follows. Bodies, which are moving under the sole influence of a gravitational field, receive an acceleration which does not in the least depend either on the material or on the physical state of the body. For instance, a piece of lead and a piece of wood fall in exactly the same manner in a gravitational field when they start off from rest or with the same initial velocity. This is a phenomenon that Galileo already explained with his experiments of bodies rolling down a smooth slope. But it is because this acceleration happens at the same rate for all falling bodies, no matter what their weight, that an equality of gravitational and inertial mass can be postulated. So if, as we find from experience, the acceleration is to be independent of the nature and the condition of the body, and always the same for a given gravitational field, then the ratio of the gravitational and the inertial mass must be the same for all bodies. Of course, as I said, this insight will lead Einstein to a second claim that the acceleration due to gravity is the same as the state of rest. So it is quite a given fact that gravitational and inertial mass are actually different, but for Einstein, they are actually both the same. But Einstein will also claim the same thing in terms of uh, in terms of uh, uh, acceleration due to gravity and state of rest. Okay. So Einstein's first paper on this subject was published in 1907, and 13 years later, he commented that while writing it, a thought came to his mind, the happiest thought of his life, he says. And I quote, "The gravitational field has only a relative existence, because for an observer freely falling from a roof of a house, at least in his immediate surroundings, there exists no gravitational field. For somebody finding himself in a free fall movement, this fall is experienced as a state of rest as long as he shuts his eyes. This implies that a state of rest is indistinguishable from acceleration due to gravity." So in his popular exposition of relativity, Einstein brings this insight home to his readers with the help of what has come to be known as the Einstein elevator. What is this Einstein elevator? The Schriver explains, this is a closed box sitting in space somewhere which can be tugged, say, up by someone outside pulling on a rope attached to the roof with a constant force, so that the box is constantly being pulled upwards. In the first moments, The occupants of the elevator will feel pressed down towards the floor, but after a while, they are unable to distinguish whether they are in a state of acceleration or at rest. Einstein uses this example to demonstrate the equivalence of acceleration due to gravity and a state of rest as experienced by the occupants of the elevator. He does this in two steps. One of the occupants drops a ball and sees that it goes right down to the floor of the elevator in an accelerated relative motion. The same is true for objects of different weight. Relying on his knowledge of gravitational fields, he infers from it that the box must feel the effect of a gravitational field. B, realizing this, he begins to be puzzled as to why the box does not fall into the gravitational field. And at that moment, and just by chance, he looks up at the ceiling of the box and perceives there a hook on which the rope is attached that pulls the box upward, and comes to the conclusion that the box must be suspended at rest in a gravitational field. Ought we to smile at the man, Einstein asks, and say that he errs in his conclusion? I do not believe we ought to if we wish to remain consistent. We must rather admit that his mode of grasping the situation, violates neither reason nor known mechanical laws. Even though it is believed being accelerated, we are nevertheless regard the box as being at rest. And that's our experience when we ride the elevator, right? We also feel that it doesn't seem to be moving, but it is already moving, especially if you've been to the skyscrapers. The tallest building I've ever been in my life is Taipei 101. In Taipei 101, at a certain point, you only feel the buildup of the pressure on your ear, but you'd be shocked that you're already hundreds of floors above the ground that quickly. Everything from that top seems so small. Einstein calls attention to the fact that this double interpretation, being in a state of accelerated motion and being at rest, is only possible because of the special property of the gravitational field of giving all the bodies, whatever their mass, the same rate of acceleration. If this property did not exist, the man in the accelerated box, the elevator, would not be able to interpret the behavior of bodies around him on the supposition of a gravitational field, and he would not be justified on the grounds of experience in supposing his reference body to be at rest. The equivalence of acceleration and state of rest resolves also the problem that Einstein initially brought up, namely that being at rest would be incompatible with an accelerated motion. And here he comes back to the story of the observer in the railway carriage who experienced a jerk forwards as a result of the application of the brakes, and concluded from this that the carriage was suddenly accelerated or retarded. Yet, Einstein writes, the observer is compelled by nobody to refer this jerk to a real acceleration of the carriage. He might also interpret his experience thus: my body of reference, the carriage, remains permanently at rest. With reference to it, however, there exists during the period of the application of brakes a gravitational field which is directed forwards, and under the influence of this field, the embankment, together with the earth, moves non-uniformly. And this accelerated motion of the earth causes the jerk that was felt. So with these illustrations of the elevator, of the train or the carriage, Einstein made it clear that in the general theory of relativity, with its special focus on acceleration, the basic equivalence principle that was laid down by Galileo also holds that the physical laws remains unchanged if we pass from a stationary to a moving frame of reference. And this means in the concrete that the effects of a uniform constant acceleration on an observer or on his measuring instruments are in fact indistinguishable from, that is equivalent to, the observers being at rest but acted on by a uniform field of gravitation. Yet, whereas in the special relativity, such an equivalence was reached on the basis of the constancy of the speed of light. In the case of general relativity, this equivalence obtains on the basis of the constant effect of the gravitational field. This difference in background will create a new problem, and that's the problem of the bending of light. In the slides that I prepared, there is supposedly a clip here about the bending of light. Uh, but I suspected that it's a copyrighted link, and it actually comes from the Genius clip of Albert Einstein from the National Geographic. And here he will show to you how the light bends. And to explain the bending of light, which is really also is very, very important concern, he will have to use the eclipse in Mercury, because when the eclipse happen, the dots just reappears and the stars just reappears. And I hope I'll send the copy of the PowerPoint, or I'll put it there in the description of this video, so that everybody can access it nevertheless. No? Let's go back to the text of what is that bending of light. No? So the special theory of relativity started from the assumption that light is rectilinearly propagated. Rectilinearly. This assumption can no longer be upheld in the context of general relativity, for in it the power of the gravitational field is such that it makes the straight rays of light curve. Light curves. No? This phenomenon is known as the bending of light. This is illustrated as follows, and this is from Jeremy Bernstein's Einstein. Let's read that. Let us imagine the following situation. An elevator is attached to its rope and being pulled upward with a constant force and hence a uniform acceleration. We are stationed outside the elevator in the rest frame with respect to which the elevator is accelerating. We now fire a beam of light from our rest frame into such a way that the light enters the elevator by a very small window, if you will, on a trajectory that is initially parallel to the elevator floor. What we will observe happening is the floor of the elevator accelerating upward towards the light beam. To us, in our rest frame, the light ray follows a straight line, while to the people in the elevator, the light beam will appear to have been bent down towards the floor in an arc. If they do not know that they are being pulled up, they can, according to the principle of equivalence, conclude that there is a uniform gravitational field in their region of space, which is bending the light downward in a curved path. The bending of light is again very strange, since according to Newtonian physics, gravity only acts on material objects with mass, whereas light is apparently massless. So if one knows, however, about the formula E_mc squared, which posits the equivalence of energy and mass, then this strangeness recedes. A beam of light transports energy, and on this basis, it can be bent down by the gravitational field. Rays of light are propagated curvilinearly in gravitational fields. This finding, however, leads to an apparent conflict with the special theory of relativity, which rests on the assumption of the constancy of the speed of light. Yet, a curvature of rays of light can only take place when the velocity of propagation of light varies with position. So the more a ray of light curves, the slower it goes, which means that it will travel slower than 300,000 kilometers per second. So the special theory of relativity cannot claim an unlimited domain of validity. Its results holds only so long as we are able to disregard the influences of gravitational fields on the phenomena of light. On the other hand, what the special theory of relativity tells us about the constancy of the speed of light has a tremendous research value. It allows us to realize the dramatic changes brought about by the presence of gravitational fields. In the example of the transmission of light, we have seen that the general theory of relativity allows us to derive theoretically the influence of a gravitational field on the course of natural processes, the laws of which are already known when a gravitational field is absent. It is thanks to the insights gained from the special theory of relativity that the general theory of relativity can develop, and therefore must be understood as a limiting case. The bending of light is an experimentally tested claim. According to Einstein's calculations, a light ray passing closely by the sun's surface would undergo a deflection of 1.7 seconds of arc under the influence of the sun's gravitational field. This deflection can only be observed during a solar eclipse. And in 1919, two expeditions equipped by the Joint Committee of the Royal Society and the Royal Astronomical Society in London, one in Sobral in northern Brazil and the other one in the Isle of Principe in the Gulf of Guinea off West Africa, succeeded in making photographs of the eclipse on May 29 that year. The results of their measurement confirmed Einstein's prediction of the light rays deflection. And this leads us to the warping of time and space. I'm sure you saw the PowerPoint, and here you'd see how time is warping. And in this video, you'd see how something will cross over, and that crossing over will actually constitute a bending of light. And I'd like to go back to the text of the Schriver because he explains this one beautifully. Given the special role played by gravitational fields in the general theory of relativity, Einstein needed to elaborate a new concept of geometry, one that more drastically than Minkowski's geometry of four-dimensional space departs from Euclidean geometry. So the system of straight lines and coordinate time used in Euclidean geometry is no longer workable for accelerating or rotating frames of reference. So if in a first move, Einstein shows the Euclidean geometry no longer holds in the case of a rotating disk. And let's look at this one. If one measures the circumference of a rotating disk and divides it by the diameter of the disk, one no longer gets the celebrated number known as pi, 3.1415, as to be expected in the Euclidean universe, but a number larger than pi. This proves that the propositions of Euclidean geometry cannot hold exactly on the rotating disk, nor in general in a gravitational field. Hence, the idea of a straight line also loses its meaning. And second, if one places two identical clocks, one on the circumference of a rotating disk and one close to the rotating disk's center, and compares the registered times, it turns out that the clock on the circumference runs slower than the central clock. From this state of affairs, Einstein concludes that it is not possible to obtain a reasonable definition of time. On our circular disk, or to make case more general, in every gravitational field, a clock will go more quickly or less quickly according to the position in which the clock is situated or at rest. When both idea of a straight line and of coordinate time becomes meaningless, especially in the context of accelerated motions, then a new non-Euclidean geometry will be required. It is there where you will find the Gaussian coordinates. Following the lead of Gauss, Einstein sets out to construct a non-Euclidean continuum in which Gaussian coordinates play an important role. Euclidean coordinates is a space in which one can reach any point by first reaching a nearer point, and in which it is taken for granted that the points are linked to each other by straight lines from which adjacent squares can be formed. In an Euclidean continuum, on the contrary, will be formed by curved, arbitrarily chosen intersecting line, which is actually called the Gaussian coordinates. So when working with Gaussian coordinates, one no longer assumes the distances can be measured with rigid rods and time sequences. Such measurements only hold for the Euclidean flat geometry. It is in this flat geometry that the angle sum of a triangle, for example, is 180 degrees. Besides this, there are geometries for curved surfaces. In the geometry developed by Riemann, all triangles have angle sum greater than 180 degrees. One, therefore, can visualize this as the geometry with positive curvature, like a sphere. In the hyperbolic geometry of Gauss, all triangles have angle sums less than 180 degrees. One can visualize this as a geometry of negative curvature, shaped something like a funnel or even a saddle. It is the geometry of negative curvature that challenged Einstein. This principle now reads, all Gaussian coordinate systems are essentially equivalent for the formulation of the general laws of nature. The Gaussian coordinate systems are very flexible then. They move in a way whatsoever and may suffer all possible alterations during their motion. Nonetheless, the flexible coordinate systems can be used as reference bodies with equal right and equal success in the formulation of the general laws of nature. And that's what you actually see, here in the Gaussian system, where you see also the bending of straight lines. So what does this lead us to is a very interesting question to raise at this point. And it is at this point also that we also see Einstein's post-Newtonian cosmology. Obviously, Einstein's new interpretation of gravitation, his accurate calculation of the recession of the orbit of Mercury, and his prediction of a non-static universe are his major contributions to cosmology that we cannot ignore right now. And we begin specifically with this concept of gravitation. Newton avowed that he did not exactly know what gravitation was, but that in spite of this, he was able to formulate the equation that ruled its effect. Based on the Newtonian equation, he could predict the velocity with which each of the planets orbits the sun on their elliptical trajectory. Newton's equations are still essentially valid and continue to be used for rough calculations. But Einstein's approach is more refined. In Einstein's new approach, the equations of Newtonian gravitation are replaced by a new set of equations that retain their form in all possible coordinate systems, both accelerated and uniformly. So Einstein made the revolutionary suggestion that gravity is not a force like other forces, but is a consequence of the fact that space-time is not flat, as had been previously assumed, but curved or warped by the distribution of mass and energy in it. Whenever in the universe, there's a significant amassment of mass and energy, Gravitational fields make their appearance, and this leads to the warping of space and the slowing down of time, as you can see in this image in front of you. If one takes our sun, then it is evident that its mass and energy make the surrounding space adopt a hollow curvature. This concept of warped space would have been completely incomprehensible to Newton because for him the force of gravity pierced through the void and used its power to maintain the planets in their orbits. Not so, not so for Einstein, for whom the planets do not follow circular or elliptical paths on a flat plane, but rather follow a straight line within a curved region of space. That's why it say bodies like the Earth are not made to move on curved orbits by a force called gravity. Instead, they follow the nearest thing to a straight path in a curved space, which is called a geodesic. Geodesic. This is rather like watching an airplane flying over hilly ground. Although it follows a straight line in three-dimensional space, its shadows follow a curved path on the two-dimensional ground. The curvature of space caused by the gravitational field generated by the sun's mass or energy is, so to speak, the natural milieu in which the planets move in quasi-straight lines. The nearer they are to the sun, the faster will they complete their journey through the path of curved space. The second contribution is the movement of or the recession of the orbit of Mercury. In Newton's universe, each planet orbits the sun along an elliptic path. The sun is not located in the center of the ellipse, but slightly off-center, so that two areas can be distinguished. The perihelion, or that part of the ellipse that is closest to the sun, and the aphelion, or the part that is farthest away from the sun. Newton had already observed that after one orbit, the planet did not return exactly to the same place. After each journey around the sun, the planet's aphelion slightly receded from its previous position. Newton realized that this recession was due not to the sun's attraction, but also to the attraction that the other planets exerted on the planet in question. This recession was the most visible in the case of Mercury, the planet closest to the sun. Each time the planet went once around the sun, it returned to a different point in space, so that the orbit, if viewed long enough, would look something like a petal of a flower, as you can see in front of you. This was an occasion for Newton to calculate the recession of that planet. He ascertained that it would take Mercury 64 years and 286 days to return to its original position. But with the help of his field equations, Einstein made the same calculations and discovered that Mercury's return to the original position would actually take 182 days less. This data will eventually be confirmed by subsequent astronomical observation. Lastly, here you can see Newton's fixed space and Einstein's understanding of space mass. But our concern is the prediction of a non-static universe, which we will see actually in the few sessions next. Whereas Newton still retained a picture of the world in which the solar system was the center of the universe, Einstein laid down the foundation for a universe that has no proper center. When elaborating in 1917 the equations representing the whole of the universe, he started from the assumption that at large scales, the universe is homogeneous and isotropic. These assumptions had far-reaching consequences. They in fact annulled the central position previously ascribed to our central solar system. In the words of Stephen Hawking, he'd say, now at first, all this evidence that the universe looks the same whichever direction we look in might seem to suggest that there is something special about our place in the universe. There is, however, an alternate explanation. The universe might look the same in every direction as seen from any other galaxy too, but it would be most remarkable if the universe looked the same in every direction around us, but not around other points in the universe. But there is more to it. Einstein's equations predicted a universe that was not static, but caught up in the process of continuous formation. And his equations represented universes that were either expanding or contracting. There were no solutions representing a static universe. That's why in 1917, when Einstein was elaborating his equations, the telescopes were not yet strong enough to explore parts of the universe outside our own galaxy. So since the predicted expansion was not observable within our galaxy, Einstein felt compelled to modify his equations in such a way as to allow solutions describing a static universe while still preserving the geometrical character of his theory. The next generation of scientists would demonstrate that such a modification was not necessary and that what original equations predicted as an expanding universe was in fact the true picture of the world. Thank you for listening. Again, if you haven't subscribed, shared, or liked this video, please do so to keep the channel ongoing. This is again Samo't sa simula. Thank you very much for listening.